it's Solomon39 again and welcome back to another video. In this video, we'll be talking about silicon and its use in transistors. Let's get started! Silicon's properties aren't just limited to the kitchen. Silicon is an integral part of computers and plays a vital role in their function, acting as a gate that allows electric current to flow past it as part of the transistor. This is the basis of computing and is what allows computers to function. Before transistors, scientists working to study electricity needed something called a vacuum tube, which amplified the charge so scientists could use it to study electricity. However, vacuum tubes were brittle and expensive. The tungsten wire in the vacuum tubes could snap, and the cathodes in the vacuum tubes would, over time, slowly become poisoned from gas molecules from other elements that limited its ability to conduct and amplify electricity. This made working with electricity frustrating and expensive. However, this is all going to change all thanks to William Shockley, John Bardeen, and Walter Brattain. The reason why vacuum tubes were used for such a long time was due to their properties. Despite being an encumbrance to the engineers who used them, no other piece of equipment could do the same that the vacuum tubes could do, amplifying the electric current while keeping the current flowing in only one direction.
This is a diode, the typical two-element electronic tube. Let's get inside it. In fundamental operation, it resembles an ordinary single-pole switch. A switch that can connect, for instance, this battery and its motor load. One power lead comes to the anode, the other lead goes to the cathode. When this switch is open, the contacts are insulated from each other by a vacuum, or by some inert gas inserted into an evacuated tube under low pressure. To close this switch electronically, all we need do is heat the cathode and give the anode a positive potential. Then here's what happens. As electrons are emitted from the surface of the heated cathode, being negatively charged, they fly at tremendous speed to the anode. In this way, a current-carrying path is formed, which closes our electronic switch and permits our motor to operate. You'll notice, by the way, that the direction of electron flow is contrary to the orthodox concept of current flow from plus to minus. In the first place, we can rectify current with it, converting AC to DC. We can do this merely by connecting an electronic tube in series with an AC circuit. As you study this circuit diagram, note that only each positive half wave of AC voltage will now produce a current. When the anode is negative, the electrons are repelled and no current flows. In other words, because only the cathode can emit electrons, we have here what amounts to a one-way street. We can visualize the result of the tube's rectifying action with the aid of these two oscilloscopes. The one on the left shows alternating current coming in. The one on the right shows pulsating direct current going out. The applications of this basic rectifying principle are many and important. The second basic thing we can do with it is amplify. Here's how. Between the cathode and the anode of the two-element tube, which we diagrammed a while ago, we now place a grid. To this grid, we connect an input of some weak voltage which we wish to amplify, perhaps that of a faint radio signal from halfway around the world. Now let's see what happens. Every time a negative potential is impressed on the grid, even though it be very minute, it has a large effect in reducing the number of the negatively charged electrons which would otherwise keep flying from cathode to anode. Conversely, when the grid is positive, an equally large effect is exerted in increasing the flow of electrons from cathode to anode. The important thing to note here is this. A small amount of power applied at the grid is amplified into a large amount of power in the anode or work circuit. This amplifying property of the three-element electronic tube is put to work in innumerable ways.
However, despite how much the engineers searched for an alternative, it was hard to come by and couldn't pull the same double duties that the vacuum tubes could, being both an amplifier and a one-way gate for electricity. Many engineers tried to find a solid alternative to the fragile and cumbersome vacuum tubes. On the other hand, they were a crucial component of the early computers. The triode, a modified variant of the vacuum tube which had a mesh in the middle between the cathode and the anode, allowed the computer to function by adjusting the mesh. The positive charge attracted the electrons and the negative repelled, giving results of 1 and 0 respectively. The mesh could change charge quickly, allowing the computer to perform calculations much faster than a human could. This is what allowed ENIAC, an early computer, to perform multiple calculations and aid the war effort for the Second World War and eventually the Cold War. It could calculate trajectories in 30 seconds, which took a human 20 hours to calculate, and is extensively used in the development of the hydrogen bomb. ENIAC, or the Electronic Numerical Integrator and Computer, used 18,000 of these tubes, which, along with the other components, weighed 30 tons and was the size of a tennis court. The thousands of vacuum tubes meant that ENIAC consumed enough electricity to power 15 houses for one day in an hour. There would often be numerous failures within the system, especially when some of the vacuum tubes broke. Nowadays, anything that ENIAC can do can all be fitted on a small computer chip the size of a fingernail with millions of transistors integrated in it. The computers that we use often nowadays are many times more powerful and more efficient than the earliest computers. Even if the vacuum tubes were cumbersome and heavy, that didn't stop progress from being made with them. Henry Moseley, who studied under Ernst Rutherford, two eminent scientists who lived in the late 19th to 20th centuries, made the most momentous discovery of his career with a vacuum tube at the University of Manchester. Placing the elements in the tube, he ionized them with X-rays and plotted the square roots of the spectra against the atomic numbers, which showed a steady incline in line with the spectra. This was the first tool that the chemists had to identify and confirm the discoveries, and was used by Moseley himself to prove many of the element hunters wrong about the discoveries, and led to the tightening of conditions and requirements to be met in order to announce the discovery of a new element. Early televisions, radios, and telephones all relied on vacuum tubes and triodes, as they could switch between the outputs quickly just by the turning of a switch that determined the gate's electrical charge. The idea for a solid-state transistor came in as early as 1924, when the Austrian-Hungarian physicist Julius Edgar Lilienfeld filed for patents in the US and Canada detailing the construction and operations of the transistors, which worked in a similar manner to today's field effect transistors or FETs, which use electric fields to control the way that charge flows through the transistor. However, the patents did not detail a process to make or construct the transistors, nor did they detail a working prototype, making the patents ignored as well as relatively unknown. After the Second World War, research and development boomed, with companies and universities spending large amounts of money on research and development, which led to a large number of discoveries and inventions being made in that period. There, an employee of Bell Laboratories called William Shockley stepped onto the stage. As the leader of the solid-state transistor research groups at Bell, Shockley, Bardeen, and Brattain worked together to produce the world's first solid-state transistor as a team. At first, the team used semiconductors indiscriminately in different configurations and with different materials to make the transistors, making failed prototypes of the FETs. However, these all failed due to a phenomenon called surface states, a hypothesis coined by Bardeen in one of their frequent group discussions. These states happen on the surface of the semiconductor material, preventing the electric field from going further into the transistors. This effect only happens on the uppermost layers of atoms with the semiconductor material because the atoms there behave differently, similar to the state they behave in a vacuum, causing the transistor to fail. Shockley originally used silicon as a semiconductor substance, but that failed. So the team looked down at the next element from it, germanium. Germanium transistors turned out to be the success that the team needed to make the solid-state transistors. With its high electron mobility and similar properties to silicon, it was a win-win for the team. In 1946, a year after research started on the transistor, Bardeen published a paper on the group's theories on surface states to the paper Physical Review, and several more followed, some co-authored with Shockley. Eventually, the team applied for 4 patents without Shockley's name, despite contributing to the group efforts in making the transistor. Shockley also contributed his knowledge of the field effect, although that was independently discovered by Lilienfeld when he filed for his patent. Shockley promptly reinserted himself into the semiconductor pictures, quite literally. What had once been a friendly group dynamic turned into a fierce battle for recognition. Shockley would often appear in the photos as the main scientist behind this operation, forcing his hand on the equipment and making Bardeen and Brattain look like mere assistants, not the brains of the operations and the ones who proposed the ideas in the first place. Despite Bell Labs' intervention, the media only saw what Shockley presented. This disgusted the rest of the team. Bardeen quit Bell Labs and went on to conduct research on superconductivity, which he later won a Nobel Prize for. Brattain was moved to another team and eventually moved to another lab, the both of them never conducting research on transistors ever again. However, though germanium has its perks as a semiconductor, it also had some major flaws. The first was that the germanium transistors would overheat easily, hindering and eventually stopping the circuits from working. There was also the question of cost, as germanium was 5 times as expensive as silicon, which was cheaper than dirt as it was so common. So, even though the transistors were a good replacement for the vacuum tubes, engineers and researchers alike dreamt of using silicon instead of germanium. In 1954, 9 years after the first transistor was made, Gordon Thiel made the world's first silicon transistor at Bell Labs. Thiel's invention changed the electronics industry, banishing germanium to the dust and replacing it with silicon. In 1958, Jack Kilby, an employee at Texas Instruments, invented and patented the integrated circuit, paving the way for the computers we see in our modern world. The invention of the integrated circuit eliminated the tyranny of numbers, which limited the performance and efficiency of computers designed by engineers because of the sheer number of wires and components in those early computers, which are all prone to fail and human error. Computers are programmed using Boolean logic, which have only 2 outputs, true and false, which correspond with the binary values of 1 and 0 respectively, which can be expressed as on and off thanks to the transistor. From these 2 outputs, we can string them together to make logic gate circuits that produce outcomes of 1 and 0, or true and false. These logic gates can be strung together to perform simple programs, which are the core of the computer. Data is collected and compiled into the same forms of 1s and 0s for storage and transfer. This is central to the function of the computer and is how the computer can perform the thousands of calculations needed to make it work. Transistors work in a number of different ways. They can amplify electrical current and work as switches for the current. To understand how a transistor can do this, we need to consider the design of the transistor. Transistors are made out of 2 kinds of silicon sandwiched between each other, the p-type or positively charged silicon and n-type or negatively charged silicon, which make it either more negatively or positively charged so that they either emit electrons, making a negatively charge or attract them, as well as an emitter, a collector, and a base. These silicon wafers will not only conduct electricity in one way and not another, eliminating the chance of the electric current flowing both ways, as is what happens when there is only one type of charged silicon in the transistor. This makes a diode one of the core aspects of LEDs, or light-emitting diodes, and a component of many electronics that only allows the electricity to flow in one direction. One wafer of the p-type silicon is sandwiched between 2 n-type silicon wafers where the base is set. The emitter and the collector are on either side of the p-type silicon wafer. Because of an effect that happens on the surface of each silicon wafer called the field effect, there are special interactions between the 2 called the p-n junction. If the electric current that comes from the emitter is higher than a certain threshold, then the current will pass through. However, if it is lower, the electrons will not pass through, making it a gate for electricity that is controlled by the voltage of the current. This is the basis for the metal oxide field effect transistor, or MOFET, as it uses a metal oxide as a semiconductor. The bipolar junction transistor works similarly, but it relies on the current instead of the voltage. Shockley's bipolar junction transistor was eventually superseded by the FET in the 1960s. The MOFET is now the most commonly used transistor in the world, accounting for 99.9% of transistors in the world. All FET transistors are based on an effect known as the field effect, which was jointly discovered by Lilienfeld as well as Shockley's team at Bell Labs. It refers to the change of the conductivity at the surface of a material when an external electric field is applied to it. This effect is quite useful, especially when it comes to transistors, since the effect can penetrate deep into the material owing to the lower density of electrons that can respond. This effect is quite useful, especially when it comes to transistors, since the effect can penetrate deep into the material owing to the lower density of electrons that can respond. This effect has also been used in many transistors and diodes, such as the previously mentioned MOSFET transistor, as well as the MESFET or the metal semiconductor FET, which uses a metal semiconductor junction instead of the usual PN junction. The main difference between these two types of transistors is that the MOSFET usually needs the voltage to be greater than the threshold in order to pass the gate that would allow the current to pass, whereas the MESFET is usually on when a current is applied to it and will only turn off if a larger reverse voltage would be applied to it. The MESFET can be used for a variety of applications in many systems. The main applications are in military communications, where the transistor is used in their radar systems as the front end of the low noise amplifier. It is also used in satellite communications and in commercial optoelectronics, or the study of electronic devices that sense, manipulate, and store light. The point contrast resistor, the first transistor that was invented and the one developed by Bardeen and Brattain, works differently. At 1.5 inches in height, the first transistor was huge. It worked because the gold leaf separated hair's width apart, would skim over the surface of the germanium, leaving the surface ever so slightly negatively charged. A small positive current would then be applied to one of the wafers and would that amplify the current. The change in positive current applied to the first wafer would mean a larger change to second, giving it amplifying powers. However, this type of transistor was harder to produce and was later superseded by Shockley's patent for the bipolar transistor. Nowadays, transistors are used in almost every computer and appliance, all thanks to Shockley and his team of engineers at Bell Laboratories. In 1956, Shockley, Bardeen, and Brattain won the Nobel Prize for Physics for the surface field effect, and Bardeen won the Nobel Prize for Physics again in 1972 for BCS theory, along with Leon Cooper and Robert Schefferer. Shockley faded from the public limelight, his downfall hastened by his support of eugenics, a discriminative set of beliefs that were based on the hypothesis that desirable traits could be bred into the human genome, like how dogs are bred for their most desirable traits. He lost all his credibility with the public and eventually faded from the public eye. The transistor was one of the most important inventions of the 20th century. It allowed for the new computer age to take over the world and paved the way for many new discoveries, especially those of the 1990s. Since the first leap that happened at Bell Labs, many more have come. Now, transistors take many shapes and forms and have taken on many roles. However, this is not the end for the transistors. Despite silicon being the material of choice for many transistors, many are switching their focus to new materials that will pull silicon's duty but faster, making faster and more efficient computers for the next generations. Graphene, the material that Professors Andrew G.M. and Kostya Novoslov discovered at the University of Manchester, has been proven to have properties that are similar to the bipolar transistor. Graphene also has properties that, due to its extreme thinness, could become a component of a quantum computer's memory. There has also been research regarding a similar 2D molecule, molybdenum sulfate. Researchers at Stanford University managed to make a molybdenum transistor at microscopic levels. There are even plans to reincorporate germanium into the silicon computer chips once again because of its superior electromobility despite the danger of overheating. In fact, germanium has already been incorporated into computer chips at IBM. Other materials are also in use, such as gallium arsenide and indium arsenide, all of which are seen as potential replacements for silicon in transistors. Vacuum tubes are even making an appearance again. Because transistors are easily affected by radiation, this can cause a problem for machinery and computers going to space, as the Earth's magnetic field protects limited protection against the radiation emitted from the sun. Computers that need to go to space need to be treated for a few years before being sent there. Otherwise, it will just stop working because the transistor's function will be hindered by the radiation. This is where the vacuum tube can come in handy. Scientists have recently devised new ways to minimize them and reduce their size to just 150 nanometers across. For context, the width of one's hair is 0.1 millimeters, making this transistor 100,000 times smaller than the width of your hair. Now, vacuum tubes are no longer the large, bulky glass tubes we envision, but small cavities in a silicon sheet. It also operates at a higher frequency as well, with estimates from the researchers standing at 0.46 terahertz, 10 times faster than the best silicon transistors. Hi, it's Lemon39 again, and thank you for watching this video. I hope you enjoyed it. Don't forget to like and subscribe to my channel, and see you in the next video. Bye!